So in today's class, we are going to talk about coordinate frames. As discussed in last class, aircraft you can think about as a robot where the link lengths can extend and can rotate. So you have combination of prismatic joint and revolute joints all the way from the inertial frame all the way to the body frame, to the stability frame, and to wind frame. But no matter what, I want you to remember the basics. The basics, uh, and we talked about these basics. The basics are the rotation transformation. And I'm gonna derive these rotation transformations once again. At least I will give you the equation because we are going to use these rotation transformations again and again as we go from inertial frame all the way to the wind frame. So in last class, we quickly reviewed the rotation about Z. And I will write this down here. So we have X, we have Y, we have Z. Now the rotated coordinate frame is X1, Y1, and Z1. The rotation, which is theta Z, is a positive rotation, and the rotation matrix R0 to R1 is given as cosine theta Z minus sine theta Z 0 sine theta Z cosine theta Z 0 0 0 1. Now let's look at the rotation about a different coordinate frame. Say now I want to look at the rotation about maybe y coordinate frame. So this is my y, x, z. And now I'm going to rotate this something like this. And this rotation is theta y. This rotation here is theta y. Again, 0, 1 rotation about y is given as cosine theta y, 0 sine theta y, 0 1 0 minus sine theta y, 0 cosine theta y. And please understand, these are the rotation matrices that we studied in robotics 1. And the last rotation, so this is going to be my x, y, z. This is going to be x1, y1, z1. The last rotation is going to be the rotation about x, and if I rotate it in the positive direction, this rotation is going to be something like this. So this is going to be theta x. So this is going to be x1, y1, z1, x1, x, y, and z. And the rotation transformation here is going to be 0 R1, since the rotation is about x, so we are gonna have 1, 0, 0, 0 cosine theta x minus sine theta x, 0 sine theta x and cosine theta x. So again, if you look at the projection of the new frame onto the old frame, you can derive these rotation matrices. When we look at the aircraft kinematics or different frames that are associated with the aircraft kinematics, we are going to use the same three frames, which are the rotation about z, rotation about y, and rotation about x. But at this point, let me clarify one super important issue. Matrix multiplication is non-commutative. What I mean by that is 0R1, I'm going to call this about z, 0R1, I'm going to call this about y, and 0R1, I'm going to call this x. So what it means is matrix multiplication is non-commutative, which means 0. So let me, for the sake of clarity, let me say RZ multiplied by RY is not equal to RY multiplied by RZ. What it means is the order of rotation is very important. So if you rotate about x and then you rotate about z, the orientation that you are gonna get is different if you were to rotate about x and then rotate about z, which means the order of the rotation is very, very important. However, if the rotations are small, then they commute. And you read this in a lot of textbooks, but it's very difficult to understand what it means. So for once and for all, I just want to address this issue. So the finite so large rotations are non-commutative. That means in general, the matrix RZ multiplied by RY will not be equal to RY multiplied by RZ. Everyone understood this? However, when the rotations are teeny tiny, when the rotations are very, very small, the product on the left-hand side equals the product on the right-hand side. What does that mean? So let me work out this math real quick, because unfortunately this point is not discussed in any robotics textbook or any flight mechanics textbook. So please understand, what do we mean by small rotations? So what I'm going to do is, I'm going to write this RZ here, which is cosine theta z minus sine theta z, then 0, sine theta z, cosine theta z, 0, 0, 0, 1. And I'm going to multiply this with Ry, which is cosine theta y, 0, sine theta y, 0, 1, 0, minus sine theta y, 0, cosine theta y. And the quickest way to do that is using MATLAB. So you can program this and actually add, just multiply, and MATLAB will give you the solution. But since we are here, just first row, first column is going to give me cosine theta z, cosine theta y. Then I'm gonna get, there is nothing else here. Then I'm gonna get minus sine theta z. Then I'm gonna get cosine theta z, sine theta y. Then if I proceed further, I'm gonna get sine theta z, sine theta z. Cosine theta z gets multiplied here, 0. Then I get cosine theta z, and then I get 0 here. And here I get minus sine theta y. I get 0, and I get cosine theta y. So this is the resultant of the multiplication on the left hand side. So what I have here is I have the resultant of multiplication on the left hand side. Did I make a mistake? Sine theta z, which first row, second column? Second row, okay, cosine, okay, second row, yeah, sine theta z, cosine theta y, correct. Okay. Now what I want to do is, I want to repeat the same exercise, but the matrices will be flipped. And if I were to do that, I don't have enough space here, but I will try to somehow manage over here. So now what I'm doing is cosine theta y, 0, sine theta y, 0, 1, 0, minus sine theta y, 0, cosine theta y. Multiply this by minus, so this is plus, so plus cosine theta z minus sine theta z, 0, sine theta z, cosine theta z, 0, 0, 0, 1. And I'm gonna write this product somewhere here. Hopefully, I will get a nice space to write this. Okay. So cosine theta z, cosine theta y, cosine theta z. Then I get cosine theta y minus sine theta z. Then I get sine theta y. Next, I get sine theta z. Then I get cosine theta z. And then I get last term here, I get 0. And the last row, I get cosine theta z, sine theta y with a negative sign. Then I get 0. And I get cosine theta y. Do you agree with me? So what I have here is this product is shown over here. So please understand, I multiplied rotation about z, then rotation about y. On the right hand side, I multiplied rotation about y and rotation about z. And now can you see that these two matrices, these two multiplications look different? You agree with me? Which means if my angles are large, the result I get from the left hand side will not be equal to the result I get from the right hand side. Everyone understood this? Which means finite rotations are not commutative. They don't follow the sequence. However, here comes the important part. Infinitesimal rotations, which means extremely small angles, are commutative. What does that mean? What is a small angle approximation in terms when we have sine and cosine term? The small angle approximation for sine is sine theta is equal to theta. Do you agree with me? Small angle approximation for cosine theta is cosine theta close to cosine of 0 is equal to 1. Do you agree with me? So what does that mean? If my rotations are small, and this is extremely important part. When my rotations are small, all the sine terms in this multiplication can be replaced by just the theta value, and all the cosine terms can be replaced by 1. Are you with me so far? So let's see what happens if we perform that approximation. So let's compare cosine theta z, cosine theta y. For small value, this term becomes 1. For small value, this term becomes 1. Do you agree with me? For small value, cosine theta y terms becomes 1. Sine theta 2 becomes theta 2. For small value, sine theta 2 becomes theta 2. Cosine theta 2 becomes 1. Sine theta y becomes theta y. And here, sine theta y becomes theta y. Sine theta y, theta 2 becomes theta 2. Cosine theta 2 becomes 1. Here, cosine theta 2 becomes 1. Sine theta y becomes theta y, 0. And cosine theta y becomes 1. Yeah. Yeah, theta z. Sorry, did I say theta 2? Yeah, theta z. So essentially, what happens is, for when the angles are small, the rotation matrices, the product of the rotation matrices equal each other. Everyone understood this? That's why the small rotations are commutative, but the large rotations are not. What is the practical significance of this? The practical significance of this is, if you have an object and then if there is a very small rotation, if you do a small rotation here, final result would be the same. But if you are going to have a finite rotation, then the results would be different. Now, what is small and what is large? Typically, small means when cosine theta value is approximately 1, and the angle usually are between 5 to 10 degrees, usually about 5 degrees. Sine theta is approximately linear up to 17 degrees, but for this commutation to work, usually the theta values are less than 5 degrees. So small angles, when you have the rotation matrices, they follow commutation. But if the matrix, if the angles are large, then the matrix multiplication, as I showed here, that this matrix and this matrix is significantly different, but they converge or they become one and the same as soon as I substitute cosine theta y is equal to 1, cosine theta z is equal to 1, sine theta z is equal to theta z, and so on. Everyone understood this? Remember this. In all the robotics books, in all the kinematics book, they write this bold statement that the small rotations are commutative, large rotations are not. But this is what it means.
In the second multiplication, row 3 column 2. Yeah, wouldn't that be sine theta by sine theta?
Sine theta by sine theta. Correct. Very good. I'm glad you caught it. Here. So did I let me see. First, okay, sine, that's fine. Sine theta y, sine theta z. Let me make the argument here and I'll say. So sine theta y, theta z. What would be the representation here? This will be theta y and theta z. Do you agree with me? Theta y itself is a small quantity. Theta z itself is a small quantity. When two small quantities multiply each other, what happens? You get a smaller quantity, which means this value gets approximated to 0. Does it make sense? So since sine theta y is a small quantity, replace as theta y. Sine theta z is a small quantity, multiplied replace as theta z. This small quantity multiplied by the small quantity becomes very small quantity, which is close to 0. That is why those angles are typically, this logic works when the angles are less than 5 degrees. Same thing happens with the other multiplication. So whenever you have two sine terms multiplying, the product is going to be close to 0. So you can approximate that as 0. Any other questions? Good. I'm glad that you point. There is one thing I want to talk to you about. And the reason I want to tell you this is because if you took my robotics 1 class, I did not explain this, but this is another cool way of understanding the rotation matrices. So what I want you to understand is, at the end of the day, what is this rotation matrix doing? Rotation matrix is actually rotating. So imagine that I have a vector. I have a vector that is rotated through angle phi, and then it is rotated through angle theta. So now what I want to do is, I have this position vector here, and this logic is very cool. So that's why I want to explain this. So this is the vector. And by the way, these notes will be uploaded on Canvas. So you don't have to note these down. Try to understand the concepts so that when you go home, you can actually add your notes onto the material that is uploaded. Now, what I want to do is, I want to find out the component of this vector. So the x component of this vector is going to be P cosine, and there are two angles, cosine theta plus C. And then the y component of this vector is going to be P sine phi plus theta. So if I want to write down sort of the position vector of this position vector is expressed as, which is shown over here, P cosine theta. So I will write it over here, P cosine theta plus phi, P sine theta plus phi, and 0. Everyone okay with this? This is the position vector. So this is the projection on x, projection on y, and projection on z. And I know the angle formula for cosine theta and sine theta. I'm going to expand this. So I'm going to write this equation as cosine theta is P cosine theta cosine phi minus sine theta sine phi. I'm just expanding. P sine becomes sine theta cosine phi plus cosine, so cosine theta sine phi, and last term is 0. Are you with me so far? So now what I have is, I have this resultant vector, and I'm gonna partition this vector into a matrix and a vector. I'm gonna partition this into a matrix and a vector. And the logic that I'm going to use is, imagine I have this intermediate vector, which is Q. Intermediate vector Q is making an angle phi. What are the sine and cosine components of this intermediate vector Q? If you look at it, so basically, if I just look at, let me take it back. Let me take it back. So what I would do is, I would actually look at the angle representing the intermediate rotation. So this intermediate vector is doing rotation of phi. I'm gonna take the phis out from this expression. So check this out. I will actually take phi out. So P cosine phi out. And here I will take P sine phi out. What it means is this matrix will become cosine theta minus sine theta 0, sine theta cosine theta 0, 0, 0, 1, and now I have here P cosine phi, P sine phi, and 0. And believe it or not, this is the rotation about z axis. So what it means is there are two ways to look at rotations, and I will talk about the point rotation and the frame rotation in just a second. But rotation matrices can also be derived looking at an intermediate step. So basically, the vector P is making an angle theta plus phi with respect to the horizontal axis. I found out the projection of P onto x and y axis, and then what I did from that expression, I kind of separated out P cosine theta and P sine theta, which are nothing but, think about it, that the vector which was at certain angle got moved over here, and I found out the component of this vector that is making an angle phi, took it out, and what is left is nothing but the rotation matrix that is rotating the vector. Again, this is just another way of representing rotation. So you can derive rotation matrices using projections. You can derive rotation matrices using the components. So this is an important concept wherein you have something called as the passive rotation, and there is something called as the active rotation. In the passive rotation, the rotation frame or the coordinate frame changes. So vector is stationary, but the coordinate frame changes. So vector remains as is, but the coordinate frame where the vector is represented changes. In the case of active rotations, the coordinate frame remains fixed, but the vector is rotated. And active and passive rotations are very commonly used in kinematics, especially 3D kinematics, and in terms of aircraft kinematics. Now I'm going to talk about 6 to 7 reference frames. So imagine, I want you to think about, it's like you have a robot, an articulated robot with maybe 7 or 8 joints. And the problem that we are looking at is how do we do the transformation from the inertial fixed frame all the way to the end effector when there are about 6 or 7 joints in between. The logic remains the same, but one thing I want you to understand, in the aircrafts, we always use something called as north, east, and down vector. So the triad, if you look at the robotics one, we always started with something like maybe Z going up, one going like this, something going like that. But in aircraft or spacecraft dynamics, we always use north, east, and down, which means the vector k is always going down. See, this vector k will always go down. And again, we use right hand coordinate frame. So curl your fingers, last two fingers. This is x, this is y, this is z. And when you have a northeast down, your north is always x, east is always y, and down is always z. So this is your x. So you are going to have x, y, and z. So you have north, east, and down. The nose of the aircraft will always be around north. So what it means is, if you have this aircraft, so I'm going to draw this aircraft. For this aircraft, this is going to be north. This is going to be east. And this is going to be down. Since north is x, east is y, and down is z. Everyone understood this? This is the nomenclature that is used in the aircraft. So the rotation about these individual frames are, if you look at the down, the rotation about down, which is curl your fingers in the down direction, you will see this positive rotation is nothing but yaw of the aircraft. So if the aircraft is yawing or if it is turning, it will rotate about the down or z direction. If aircraft is pitching up, it would have rotation about the east. So the rotation about east is pitch. This is pitch. And the rotation about north is roll. So aircraft will have three axes. This is a triad. We always use something called north NE, they call NED frame, north, east, down frame. The aircraft north is going towards the nose, the east going towards right, and down going straight down. So aircraft will have north, east, down frame. Question, yeah?
The center of mass, not center, right?
So it will be the center of mass of the aircraft. Yeah. Any other question? Yes.
When there's like the center of mass of the aircraft, if the center of mass changes, does the vehicle frame, is it always fixed at one spot in the aircraft, or can it move?
It can move, but for the time being, at least when we look at the small UAVs, we are going to assume the center of mass does not change. Everyone understood? North, east, down is going to be the frame we are going to look at. Now let's start with the very first frame. The first frame is the inertial frame. What do we mean by inertial frame? Inertial frame, you can think about the zeroth frame in articulated robots. If your robot arm is fixed onto the surface, the zeroth frame is the fixed frame. Now we are looking at UAVs that are flying close to Earth's atmosphere. We are not looking at missiles, or we are not looking at rockets. So we are going to assume the Earth is flat for the purposes of analysis. So we are going to assume the Earth is flat. So the inertial frame will be Earth fixed, Earth centered, which means you have this Earth and there is this frame, and this will be our inertial frame. So this will have one north, one east, and one down. So this will be N, E, D. If I were to look at the flat earth assumption, if I were to make a flat earth assumption, that flat earth assumption means that this spherical earth is something like a flat surface, and on this flat surface I have this frame north, east, and down, and this frame is fixed to the earth. So this is down, this is north, and this is east. Please understand, I'm still following the right hand coordinate system. X is thumb, Y is the first finger, and Z is, so I want you to kind of look at X is north, east, and down. So this is the frame, no left hand, right hand. So the GPS data that we receive from satellite is reference to earth center, earth fixed frame. What does that mean? It means when you have a GPS receiver in your vehicle, the satellites are sending all the ephemeral data. GPS receiver grabs that radio signal, does some filtering like Kalman filtering, corrects for the propagation delays, biases, timing errors, and then finally the solution that GPS receiver calculates is with respect to earth center, earth fixed. GPS receiver calculates the solution with earth center, earth fixed. And this is very important because those satellites are kind of traveling in an orbit. Satellites send the information wherein they have the time when the signal was emitted. Then GPS receiver grabs that time signal and then recognizes the time it captures the time when that signal reaches the GPS receiver. So speed of light multiplied by time gives the distance from the satellite. But that string will contain the ephemeral data, which allows the GPS receiver to resolve the position of the receiver with respect to earth center, earth fixed frame. That is the inertial frame that GPS receiver is going to calculate its current position. Everyone understood this? So our inertial frame is going to be earth center, earth fixed. And then what we want to do is, we want to describe the orientation of the aircraft. We want to know where the aircraft is located. So that is going to be my next frame. So I have this frame, and then I have this aircraft. This is something like this. This frame, please note, this is fixed. So this is my inertial frame. Then what I have is maybe this is the CG of the aircraft, and I'm going to attach my second frame, again north, east, down, my second frame to this aircraft, and this is going to be the aircraft based frame, north, east, down. So this is going to be my aircraft based frame. And please understand, this frame number 2, which is called as the vehicle frame. Vehicle frame will be attached to the aircraft. This vehicle frame will be attached to the aircraft. But there is something else I want to talk about. Since the frame I have drawn over here is slightly different, let me just the first frame, let me show you something else. So if this is the aircraft, I'm gonna take this inertial frame and place it at the vehicle frame. So think about it like something like this. And this second frame is representing the translation of the CG of the aircraft from the inertial frame. So that frame is indicating the pure translation. So think about it like, is for time being, think about it like you have a center of the aircraft, maybe a sphere representing the center of the mass of the aircraft. And what you did, you just did a pure translation of the inertial north-east down frame onto the CG of the aircraft frame. Everyone understood this? There is no rotation. The frame number 2 right now, which I'm showing attached to the aircraft, is in the same orientation of the northeast down inertial frame. Everyone understood this? Now, what we are going to do is, we are going to look at the rotations of the aircraft. So this is the vehicle frame. And I want to be absolutely clear, because this is the point where the students, I've seen students getting confused. So for my own satisfaction, I'm going to explain these concepts again. So imagine, let me give you a nicer picture. Earth center, earth fixed frame. So this is north, this is east, this is down. North, east, down. This is fixed. And now I have this aircraft. Now I have this aircraft. I want you to understand that aircraft can pitch, roll, and it can yaw. But these are the successive rotations. So first, what I need to do is, I need to translate this frame from the inertial earth center, earth fixed, to the CG of the aircraft. So now what I do is, I just do a translation of the frame to the CG of the aircraft. And this frame is called as vehicle frame. It is absolutely important to note that vehicle frame and inertial frame there is only pure translation. No rotation. Are you with me so far? Now what I'm going to do is, I'm going to represent the attitude of the aircraft. The aircraft, clearly aircraft cannot be like this. Aircraft frame can never be aligned with the inertial frame. Aircraft is going to pitch, aircraft is going to roll, aircraft is going to yaw. So what I'm going to do is, I'm going to resolve independent rotations. This concept is exactly similar the spherical wrist that we solved in robotics 1, which means now from the vehicle frame, I have the first aircraft rotation, I have the second aircraft rotation, and then I have a third aircraft rotation. So this is like, I have 3 successive rotations similar to the spherical wrist. Remember, we studied spherical wrist in robotics 1. So think about it, is like the spherical rest is attached to the vehicle frame, and the first rotation of the vehicle frame is from vehicle to vehicle one frame, which means you had an aircraft and now aircraft is yawing. Aircraft is yawing. Yaw is about z-axis. So yaw is about z-axis. So what I want you to see is, this is my vehicle frame, aircraft yard, and then I have this new coordinate frame, this new frame. So when aircraft yard, vehicle one frame is related to the vehicle frame by this rotational transformation matrix. And this rotation transformation, believe it or not, is exactly same as the rotation about z-axis. Are you with me? So I want to explain this again. So now you are in the vehicle frame and the aircraft yard. So this frame after yawing, frame after rotation about z, is your vehicle one frame. You had vehicle frame, aircraft turned or aircraft yard, and now you have vehicle one frame. Vehicle and vehicle one frame will be having the rotation matrix corresponding to the rotation about z. Yeah.
So with these three frames, in terms of these being, I'm assuming connecting at some sort. First frame, our initial frame, that is like basically our base
Fixed frame.
fixed frame. The second frame, that is more of the vehicle frame, that is
Translation. Pure translation
Then vehicle one,
is first rotation about yaw. So vehicle one is the first rotation about yaw. Everyone understood this? There is a subtle part which I want to talk about vehicle one frame. And if you look at vehicle one frame, this is the exact same rotation matrix that you use when the rotation is about z. The only difference is, I want you to understand this. Which is our old frame? So I have two frames, which is very important because there is an issue with the sign and I want to be absolutely clear and explain it to you what that is. We have an old frame and we have a new frame. Which is my old frame? Old frame is vehicle. The aircraft yard or rotated. What is my new frame? My new frame is vehicle one. So if I were to write my rotation matrix using the sign convention that we used in robotics 1, or as a matter of fact, the rotation matrix which I just derived, which is, this is old and this is new. So this is going to be, old is going to be vehicle frame and the new is going to be vehicle one frame. Are you with me so far? And this rotation matrix is absolutely important, so pay attention. This rotation matrix, since the aircraft is yawing, the yaw is the positive rotation about z. So I would write this something like psi, 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 and psi. Do you agree with me? Now, please understand, you have the rotation is from the vehicle to vehicle frame. And as you can see, the rotation matrix is cosine psi, sine minus sine psi, and cosine psi. But if I want to go from vehicle one to vehicle frame, so instead of vehicle to vehicle 1. I want to flip the order. I want to flip the order. What would happen to that rotation matrix? Rotation matrix will get transposed. Remember in last class we talked about it. Once again, in this particular case, the old frame is vehicle frame, new frame is vehicle 1 frame, and these two frames are related with the yaw of the vehicle. The aircraft is yawing. Yawing means like this, turning about z-axis. But if I were to flip vehicle 1 to vehicle frame, that rotation matrix will be transposed. Everyone understood this? Which means the negative sign term, which is on first row second column, would go to second row first column. Are you with me so far? So now I want you to look at the transformation that is shown over here. This nomenclature, and I want to be clear because if you use the book, the nomenclature is slightly different. This nomenclature is rotation of V1, which is the vehicle 1 with respect to vehicle frame. This is vehicle 1 frame, and this is vehicle frame. So can you see that sign term is transposed? Are you with me so far? I would explain this once again. So please understand, when we derived the rotation matrices, the way we related the transformation is the old frame transformed to the new frame. And this is the transformation matrix that we got: cosine phi minus sine phi, sine phi, cosine phi. You can derive the kinematics equation with these expression as well. But for some reason, if you read the book, they represent the exact same transformation, something like this is the old transformation and this is the new transformation. So our rotation transformations, so what he's showing, it just transpose of what we have derived. Everyone understood this? Yeah.
So when we want to say like what type of like when we're trying to explain what our transformation is, when we denote it, we would always have the old frame at the top left and the new frame on the bottom right.
So if I'm going from old frame
Right.
to new frame, I get a transformation. But now if I want to swap, I want to go from new frame to old frame, I need to transpose the rotation matrix. And this may be like there are few more transformations coming. But what I will do is at the end of the day, by next week, I will actually use MATLAB and I will derive these transformations. But I want you to understand what is happening. So we took care of the first transformation. Do you agree with me? Now comes the second transformation, which is now I'm going from vehicle 1 to vehicle 2 frame, which means I had a vehicle frame. I yawed the aircraft. I got into vehicle 1 frame. Now I'm going to pitch the aircraft, and that takes me from vehicle 1 frame to vehicle 2 frame. Do you agree with me? Pitching is the rotation about, as you can see, pitching is rotation about y, which means what I would do is I would go to the rotation about y and I would replace theta y's with theta. I would represent theta y with theta, and that would take me, and this is very important, vehicle 1 frame to vehicle 2 frame. Are you with me so far? So now what I did, this is exactly like spherical wrist. So first rotation is about Z. Second rotation is about Y because the aircraft is pitching. And the third rotation is about X where the aircraft is rolling. So what happens is you go on to the vehicle 2 to the third rotation, which takes us to the body of the vehicle. And vehicle frame, your rotation, vehicle 1 frame, pitch rotation, vehicle 2 frame, roll rotation, and now we are at the body of the aircraft. And I'm going to write this again. So how did we start? We had an inertial frame. Inertial frame, we translated inertial frame. It is pure translation that gave us vehicle frame. We rotated the aircraft about yaw, which is yaw. We got vehicle 1 frame. Then we pitched the aircraft about Y. So this is the rotation about Z. This is the rotation about Z. This is the rotation about Y. So we got this theta, which is pitch. We got to vehicle 2 frame. And from vehicle 2 frame, what we did, we rolled about X, and that rotation is phi, and that is roll, and we went to the body frame. Now, if you want to understand the similarity between this whole thing is nothing but spherical wrist. Which means if I multiply the first rotation transformation about Y, about Z, with the rotation pitch transformation about Y, multiplied by the roll transformation about Z, X, then when I combine these three, what that means is I had an aircraft that started with an inertial frame, earth center, earth fixed, flew to a certain distance. This is where my vehicle frame is. I yawed the aircraft, vehicle 1 frame. I pitched the aircraft, vehicle 2 frame, and I rolled the aircraft, and now I am in body frame. Everyone understood this? Yes.
Little confused with the second point, which is that the pure translation and no rotation. This is essentially a rotation.
No. So whenever you have a complicated motion, we have to kind of partition the motion into translation and rotation. So if you think about the aircraft is clearly translating and aircraft is rotating. So what I'm assuming that my first joint is purely a prismatic joint. My first joint is purely a prismatic joint, but that prismatic joint can extend in X, Y, and Z. So my aircraft actually went here, but aircraft is also undergoing to go rotation transformation. But again, the sequence of transformation that I'm assuming, aircraft first yard. So vehicle to vehicle frame. Aircraft then pitched vehicle 1 to vehicle 2 frame, and then aircraft rolled, and that is the final orientation of the aircraft, and that is the body frame. Everyone understood this? Yes.
So as you go into different vehicle rotations, it's the only time the actual directions that of southeast west are only at the initial.
Inertial frame is going to be fixed.
Right.
And why I'm saying this concept be so emphasized, because you can build your entire career, which I did at some point, just looking at this transformation and finding out the altitude solution for aircraft, either quadcopter, fixed wing, tilt rotor, spacecraft, everything. And let me emphasize this once again. Imagine the aircraft is translating and rotating. We cannot combine these and solve all together. We need to separate out these motions. So the way, for analysis purposes, the way I'm separating out these motions are, first, that object translated. Okay, so from Earth center, that object went to certain location. At that location, the object yawed, then the object pitched, and then the object rolled. And that is the final orientation of that object. You agree with me? And these transformations, there is the first pure translation, then next is pure rotation about z, pure rotation about x, and pure rotation about y. So these are the rotations. Now, why is this so important? Because there is something called as, you have a question?
Oh, that's right.
So there is something called as strap down inertial navigation system, which means it is 3-axis accelerometer and 3-axis gyroscope. We need to know where the aircraft is, what is the orientation of the aircraft. So what we do is, we have this 3-axis gyro and 3-axis accelerometer strapped, fixed, strap means fixed to the aircraft. So which means as the aircraft is maneuvering, it is going to record the roll rate, pitch rate, and yaw rate in the body coordinate frame. Are you with me so far? Yes.
Will this work for like submersibles too?
Yes, it works for everything. And believe
sort
it-
of like three-dimensional movement.
Yes, three-dimensional movement. It works for rendering. It works for computer graphics. It works for everything. This is the crux of coordinate transformation, rotation matrices, for computer graphics, strap down navigation, three-dimensional kinematics, and so on. So you have an accelerometer and gyro that is strapped down. Strap means fixed, strapped to the vehicle. The vehicle is making some rotations, and that accelerometer and that gyroscope is going to measure the angular rate and translational acceleration. Now, with those angular rates, please note, those angular rates are measured in the body frame. The body frame is already transformed from vehicle frame to vehicle 1 frame to vehicle 2 frame to body frame. Do you agree with me? But the sensors or the sensor data in the body frame has to be used to find absolute orientation and absolute position of the aircraft. So every aircraft, fighter aircraft, tilt rotor aircraft, has something called as inertial measurement unit. That inertial measurement unit is 3-axis accelerometer and 3-axis gyroscopes. Accelerations integrated twice give you position. Rates integrated once give you orientation. So the sensor data coming from that IMU, inertial measurement unit, is integrated and fused to find out the position of the aircraft and the orientation of the aircraft. Everyone understood this? So if you just understand this, you can do your entire career on strap down navigation system. So basically, how do we find out the position and orientation of a moving object? The problem there is the sensor data is going to be noisy, because sensors are inherently noisy. Once you do integration, that noise gets multiplied by time. And please note, time continuously increases, which means your solution is going to diverge. So how do you correct that solution? For that, you need an external update like GPS. GPS is going to give you position updates. Those can be used to correct this noisy solution that you are computing. So that is why we look at something called as sensor fusion, wherein you have sensor data coming from IMU, and then you have sensor data coming from GPS, and you combine these two data sets to come up with the least square solution using something called as Kalman filtering. And we will talk about it, but I'm gonna go very slow for this first part, but please understand, this is exactly the recap of what we studied in robotics 1. The only difference is in robotics 1, our frames were fixed with respect to the joints. Now we have to assume the frames are fixed to the aircraft orientation. First, inertial frame. Inertial frame, when it is translated to the CG of the vehicle, it becomes vehicle frame. When the frame attached to the CG of the vehicle aircraft is yard, it becomes vehicle 1 frame. When the vehicle 1 frame is pitched, it becomes vehicle 2 frame. And when that vehicle 2 frame is rolled, it becomes the body frame. And all the sensor measurements that you get are in this body frame. Everyone understood this? Yes. Question?
What is the order of the rotation of the?
Order of the rotation is first rotation is yaw, second rotation is pitch, third rotation is roll. First rotation is about Z axis, north east down. So north east down. First rotation is about Z axis. Second rotation is about Y axis. And third rotation is about X axis.
What is the rotation of the?
What exactly? What if the rotations are reversed? How is this problem solved in practice? Remember, large rotations are non-commutative. Small rotations are commutative. So every time aircraft is going to rotate, the solution is propagated at milliseconds, which means the integration is carried out at milliseconds. In milliseconds, the angles do not change a whole lot, which means the commutation still exists because the angles are not changing at those timestamps. So think about the aircraft is rotating. But if you are going to perform these operations at millisecond, those rotations will be commutative. There is a problem. The problem there is if the aircraft is like maybe F-16, extremely fast, highly agile, highly maneuverable. This formulation will fail, and for that we have to use Wattonian formulation, and we will get to that formulation in next chapter. We haven't finished this, but let me tell you what's going to happen next. Right now we are at the body frame, right? But the air, once the air hits the aircraft, clearly we need to have some angle of attack. We need to have some angle of attack so that the aircraft can be lifted. We need to have some angle of attack so that the aircraft can be lifted. So clearly there is one more rotation. Do you agree with me? So now from body frame, we are gonna go to stability frame. Stability frame means the wings have some non-zero angle of attack, and that rotation is about your y-axis. Now the wind hits the aircraft. When wind hits the aircraft, aircraft slips. So basically you have something called as the slide slip, and then you go to the wind frame. So now here is the thing. Wind forces are in wind frame, right? The ground velocity of the aircraft is in inertial frame. The aerodynamic forces acting on the aircraft are in the stability frame. And finally, we have to apply Newton's law of motion. Force is equal to mass times acceleration at the center of the aircraft. But the problem there is these different forces, these different orientation and rotations are a sort of sprinkle on these different frames. Dollars to dollars, pesos to pesos. So what we have to do is we have to grab all those orientation from different frames and using the rotation transformation, transform them to a consistent frame. Once that is done, aircraft dynamics problem is solved. And let me go a step further. Once you understand this, you can solve any moving body in three-dimensional space. It doesn't have to be just aircraft. It could be missile, it could be stone, it could be rock, it could be spacecraft. Once you understand what is happening, because at the end of the day, you have to apply Newton's law. Newton's laws are vector equations. Vectors require coordinate frames. So all the forces need to be transferred to a constant coordinate frame. All the rotations, angular velocities, angular accelerations need to be transferred to a consistent frame. And then you get this differential equation that you solve, and that's it. So basically, I promise you at the end of this course, not only you can solve any aircraft dynamics problem, but you will have no problem in solving spacecraft dynamics problem or underwater vehicle dynamics problem or any robotics problem. Okay, so I'm going to stop here and we'll continue next time.